Hello, everybody. So this room is about talking about the 4680 manufacturing. It's going to be a show and tell. You have the Bitly tweet, the Bitly link in the description above to follow along. You don't need an account. Just join us. If you have questions during this episode, feel free to call in right away so we can go over these questions. You're probably not the only one that's confused at that particular point in time. So let's clear it out as we're going. I'm here on the first frame. You can probably see my pointer is probably in red or pink with Alex. This is me. And so we're going to get started. So what we're looking at here on this first image is what is called like the mother roll. This is from the Roadrunner line, which is basically 8 strips of electrode material on a copper foil. Because it's copper, this is the anode side of the battery. There's an identical roll that's made of aluminum that is used and sandwiched to make the battery. What I want to point out here is here, if I'm going to zoom in next to the guy's foot, if you see here, like each strip here makes actually like 2. So you see this from here to here, this is used to make like 1 battery. And this other part here is used to make, hold on, getting some difficulties here. Froze up on me. Yeah, here to here, that's another roll. So the copper is being split like in 2. So let me make I don't know if I can make it fine enough, but here it's split down the middle in the copper here, and it's split down here to do the flags, like the tabless architecture. And then there's a knife that splits this roll like in half, like right here. So each dark strip counts for like 2 electrode belts. So because there's 8 belts, like all of this is like for 16 batteries. So if, for example, you need 5 meters of this roll to do like the length of the jelly roll, which we'll get into soon, then each 5 meters would be good for 16 batteries. Is that like clear? Does that make sense?
Mm-hmm. Yeah.
So what's the width of each of those rolls?
Oh, I don't have the exact width of this roll. You can see down here, they say that the length is like for 12 kilometers. So it's a very, very long roll. The foil is very, very thin. And of course, like I said, this is only one component of the battery. This is like the negative electrode, the anode, because it's copper. There's a similar roll that's made of aluminum that has also dark stripes that is also going to be split in the same way. And then it's going to be assembled into a jelly roll. So if this is good, let's move on to the next step. So once they have that and they split it, I'll be uncovering here the next part. Okay, so here you can see we have the jelly roll. This is where the battery is being created. So I want to point out a few things of interest here. So I want you to see the copper right here. You see, and you see like the electrode material goes from here all the way up to here. And you can catch that same copper as it's being rolled. You can find it here. You can see all this side. And then you have the separator, which is sort of like a very thin film, which is white, which, as you can see here, it's wider than the electrode material. Because as you see, as it's being wound, you're not seeing any black part here. So it's covering up. And then behind that, this here is electrode material again, the same black stuff. And here is the aluminum. Here, the same strip where the flags are going to be, where the flags are cut, and it's being rolled. And you can see the aluminum here being rolled. And behind that, you'll have another behind here, because you have to imagine like behind, like what's behind this foil, you can't actually see it because it's like basically the same as this side. It's on the opposite side of the copper here, you will have a little bit of overlap of white separator material. And because if you look like behind this copper, behind this aluminum, which is the cathode, if you wound, you come to the white part here. So behind there, this, if you follow your eye, you would be going to another white material. So you have the copper anode and the aluminum cathode being wound with two separators. And once it's rolled, you don't see any black material anymore. Everything is covered up. The only thing that's sticking out on both ends is on a little bit of strip of aluminum here and a little bit of copper on this end, but it's also sticking out. You can see it's sticking out. Yeah, go ahead.
So you said there was two white layers?
Separators, yeah.
So where's the second one?
The second one, you have to imagine it behind the cathode, the aluminum foil. So this foil here, I'm trying to draw it.
Oh, there's two feeds coming in?
Yes, there's two feeds. And if the camera was like rotated on the other side, you would be seeing the same thing here. So the white material would be a bit wider than the foil where it ends black. But where it ends in metal, like here, you can see like you don't see any white because the copper has to stick out, same as the aluminum on this side. It has to stick out. So, but you don't see the foil because the foil, if I draw it in, well, let's say, let me use another color maybe. So the white, yeah, maybe I could take a white pen. So if the foil was transparent, I'm going to draw it in dashed line. It's probably like somewhere here behind, and it's going across this way, like behind the foil.
Yeah, I see it now.
Okay, you just don't see it in this particular photo. And I just want to point out that as you're seeing the jelly roll right now, the flags, like the aluminum and the copper, is basically sticking out. It's like part of the cylinder. And this is going to change in the next step. So if there's any questions, are we clear so far? Like one of these strips here is what we were talking about in the previous, is one of these black strips with a little bit of copper on one end. This is what we're seeing here. All right, so if there's no questions, I'll move to the next step in the process.
I think we'll just reiterate for the people who are new that popped in.
Yeah.
Feel free to call in and ask questions as we go. I think Alex said that would probably be easier. So if anything pops in your head, just feel free to call up. And for those who are just popping in, we're doing a Tesla 4680 manufacturing show and tell. So I think the best way for you to follow along would just be to click that link right above our sort of heads here, where it says with Miro whiteboard presentation. And you don't need a log in or any special info. You can just click the link on your phone or your desktop, and it should work just fine.
Yeah, thanks a lot, Sawyer. So if we're going to the next, I've uncovered the following slide. So let me take back, let's say, my red pen. You can see here, you see the same jelly roll, the white material, but they added these blue, like sticky tapes on each end. But what I want you to notice is that right here, the aluminum, and on this side, the copper, they're flat. They're not sticking out anymore. So this is where I'm going to go to the image that's like right below it. So I'm going to pan here. You can see another view here where, let me take back my pen. You can see here, it's been flattened. It's not sticking out as much. And you can see it looks like a little bit crumpled. And when you look at this cell like head on, I know it's blurry, but you can see like there's no aluminum. You can see here a little bit of the copper sticking out, just a little bit here. And this is, if you look at the last image here below, you'll see this is what I call basically the Rosetta flags. Like once it's all laid down, this is what it looks like. So you have this, each flag here was sticking out straight, like all of these little flags. that are part of the foil. They're not welded on. They're just like the part of the foil. So once we looked at the mother foil, the first picture we saw, the flags weren't cut yet. This is cut later on, just before the winding. So just before the winding, all these little cuts are being made into the foil, and they're rolled and they're all sticking out. And then there's a process that lays them all flat like that in a type of Rosetta pattern. So you end up with a flat surface on each side of the jelly roll, almost flat, not perfectly flat. So on one side, you would have like this in copper, and on the flip side, you would have the same thing, but it would look silvery because it's aluminum. Does that make sense?
Mm-hmm.
Yep.
No questions so far? You were good? All right. So I'll keep going. So let me uncover a little more. So we're going to the next step here. Okay, we have a lot to cover here. Hold on. Let me close that up here. Okay, so this is important that you zoom in with me because it's not very clear. This is from, of course, like all these images are from the Tesla official public video that they released on their YouTube. But if you zoom in here, like really, really close, and I'll take my tiniest pen, I want you to notice that we can't see the flags, but we see like these shapes, like these V shapes on the top. There's something there on top. It's not clear what it is on this photo, but the flags aren't there anymore. Something was put on top of it. And you can see it also like on this side. Is it clear? It's not really all that clear yet. Yeah, so this is basically the only photo where you can see there's a semblance of a shape. And if I go here to the bottom, this is what is called, on the aluminum side, the cathode current collectors. So you can find, again, those same shapes, those type of V shapes that are cut on the top of the cell. And this is basically just like a disc, an aluminum disc that is placed on top of the flags, compressed, and laser welded. And the laser welds are these here. These are the laser welds. So you have, for each segment, you have 5 laser welds like this. And so basically all those little aluminum flags are like fixed to this disc, and you can't separate them. So here you can see another, that's a laser weld, that's a laser weld, so on and so forth. And what I want you to notice here is that all these V's, I'm not going to draw all the laser weld, but all these V's are basically welded to the aluminum flags of the cathode side of the battery. All these little V's, like they can't come off. But then I want you to notice like the geometry that this has. Like this geometry is, all this is welded. And here you have, let me take another color. These are cuts. So this is separated. As you can see here, there's a cut. So the center part here is completely loose. And it's held, like the center part is almost like on what looks like could be like a springy type surface. So here, the center part here is not fixed to anything. It's loose, and you can actually see it on the photo that's right next to it. So let me take my pen here, and you can see here, there's a gap. See, all the triangles are welded, but you see here, there's a little flappiness. So this part here can actually move up and down. It can go move down because there's like flags underneath, like we saw, and there's also the hole in the middle of the jelly roll, like underneath here. But this thing is like movable.
Is there
and I just wanted to point. Go ahead.
Is there an advantage for it to be moving?
We'll get to that.
Yep.
Of course, like once we get to why they did it that way, then we might have some conjecture and speculations. But like this is very clear from the geometry. Like they left 6 branches. So this is like one branch, This is another branch. This is another branch. And you have one down here and you have one here. So you have 6 branches that connect to that are welded on the opposite end of the disc. Like the welds are here. Here on each segment, you have the welds. But this center part can move. And I just want to put your attention that we had already seen this. This is not like brand new, because here, this is like the photo that Electric put out a few days before Battery Day. And if you look closely and you zoom in, you'll be able to see those same triangle. So you can see here, that's a triangle. Right here, that's cut. This is another, oh, not this one, sorry. This is the flap. So you have a triangle here, like this, and you have a triangle here. I know it's not easy to make out, but they're there. All these shapes are there. So we had seen this before Battery Day. We didn't see it at Battery Day, but we saw it before Battery Day. And if you look at it, you can see like that foil is not thick. Like the thickness here is like super, super thin. Like I just drew 2 parallel lines, but it's much, much thinner than that. So, and the same thing on the flip side, on the anode side, you have the same type of situation. But the collector, the anode current collector, looks very, very different. But it's based on the same principle. So if you look here, you'll see the laser welds that are here. These are the laser welds right here. And you have 6 segments that all have the same laser welds. So these portions are fixed. Whoops, that didn't come out too good. You have like this, laser weld here, and you still have the 6 little arms. Maybe I'll take another color. Sorry, I'm not super good at this, but yeah, let's take green. So you have these little flappy arms that are also like springy-like, and that are detached, and you can see them here. They are detached. They're from the main body. And they have big flaps all on the other. So it's basically the same design as the top, but inversed. So on the cathode side, like the springy surface is in the center. This is the springy surface here, or here. That's the springy surface, the surface that moves. And on the anode side, the springy surfaces are here on the periphery, on the perimeter of the cell. So you have 6 springy sides here held out by 6 springy arms. And on the cathode side, you have 6 springy arms that held up 1 springy surface in the center. And also, this is the photo from Electric where we saw the same cell being shown. And you can actually see at least 3 of those surfaces that are on springs. So you have 1, 2, 3, and they go around. I know this is a lot. Is there anything that doesn't make sense of how the jelly roll looks at this point in time?
So, Alex, just a quick question.
Yes.
Can you see my pointer?
Yeah, I do.
Okay, so is this the part that is right on top of the picture on the left? Is this what's covering it?
Okay, so I'm gonna center it here for the people who are gonna watch the video later. Okay, so you're saying is basically this hole. Okay, so if I'm looking at this hole here, yes, this is covering. Well, it's not covering. It's leaving access to this hole right here. And if I look at this donut of like solid material that has no welds, no springs, well, this would be approximately like here.
Mm-hmm. That's right on top.
Right on top.
Right? There's
nothing in between. And the triangles that are laser welded are like, I'm just gonna, maybe not too good at drawing, but so these would be the triangles, and let me put another color, and these are like the laser welds, or would be like here.
Okay.
And going all around, and here you would have, let's say, another of those triangles like this, and you would have the springy part. Let me take another pen. Like the spring would be like here, with the surface like this on top.
So let's say you were to
Yeah.
open the cell casing. Is this the top here with the laser welds? Is that the first thing you see?
You're going. It's a good question, but you're just going one step ahead. Yeah, because I don't want to.
Okay.
I don't want to confuse people, and I just wanted you to notice, like the hole here on the cathode side. There's no access to the hole anymore. There is a hole behind here, behind the anode, but behind the cathode current collector, there is a hole, and the only way it's only on the anode side that you still have a hole. And I'll go back up top to the first picture here. Let me take a bigger pen. And here, in this photo here, you can see the anode is on top. The cathode, the aluminum disc is on top. And it's sitting, and you can see it here. There's like a pin. You see that there's a needle right here? Well, this needle, like this is a puck.
Mm-hmm.
So it's basically like called a pin puck, and you have the jelly rolls are placed on top of it. And so it goes through the hole that we saw that was left accessible on the anode side, and it doesn't go all the way up. So if I would draw it here on this one, like it probably stops about here. And the jelly roll.
Well, that makes sense. Why there's the hole?
Yes, and we're getting to that. There's probably a very important reason that there's a hole, and now we're getting into like the manufacturing and the design. So if this is clear, like jelly rolls have an access point towards the bottom and a pin just to hold them, to carry them along. If there's no questions, nobody from the audience, I hope I'm being clear, seriously. And don't feel shy to just call in if I'm not.
Yeah, you are.
You can also ask questions at the end if you want, but probably best. So I'll uncover the next step if this was clear. So now we're going to look at the can where the jelly roll goes into. Okay, this here is, and there's no like top or bottom to a can, but for ease of conversation, I'm going to call this here. Maybe I can even probably write it. So I'll call this the top. Here we go. Maybe that's a bit too big. I'll call this the top. And what do we see here on the top? Well, we see a can, and here, let me grab the pen. We have two. So we have the body of the can. That's basically this. We have a little white disc of material, and we have another metal part here. So the white little like disc is basically an insulator, because you can't have the anode and the cathode touching, or else you're in short circuit. The top part here is the cathode side. So it's the positive side of the battery. And we've been referencing this for lack of a better word, like the nipple of the battery. So this is where you get the positive connection to the battery. This is the only part you can get the positive connection. There's no other place on the battery you can get the positive connection. The negative connection to the battery is the whole rest of the can. The whole rest of the can you can connect anywhere you want. That's the negative side. This is the positive side. And if you look at how the cans are when they come onto the line before the jelly roll is put in. So you see here, the cans are empty. And they're flared at the top, and there's no jelly roll. The bottom looks like, as they are now, the top is pointing down. We're looking at the bottom. This is what I call the bottom of the can. So let me write it here. This is the bottom facing up. That's what this is here. This is the bottom facing up before the jelly roll is inserted. Does that make sense?
Yep.
Okay. So now, how do we connect these things? Because I said the whole can is like the negative pole, and only the nipple on top is the positive pole. Well, if you go to the previous images I showed, you will see that there's only a round section here that is movable, that it's the center of the can, and it's the same position as the nipple. So how do you connect this part here to the inside of this part here. So the jelly roll, when it goes into the can, goes cathode side first. So the silvery part goes down into the hole first. And the way you connect it is you go through the hole of the jelly roll here with something that goes all the way to the bottom, and you weld the center portion here that's on like springs of the cathode current collector to the inside portion of the cathode nipple. And suddenly your jelly roll is fixed. Okay, so you look at the cathode current collector here.
Can you repeat that?
Which has the springy part is just the center. This whole jelly roll goes into this can right here, this side in first. So you turn it so the cathode, like let's say on that image on top, the cathode, you point it down, the cathode current collector, and you slide the jelly roll into the can. Now you need to.
So this nipple isn't on yet?
Yeah. Hold on. Here you don't see it, but in this little cup, like the battery continues like this, and the nipple is right here. You don't see it, but that's where it is.
Okay, so you're just putting the jelly roll in.
Yes.
The jelly roll just is going in.
Yeah, I'm trying to do it 3D, but the nipple is there. It's just you don't see it.
No, you are.
So this goes in.
Yeah.
The cathode current collector goes in first, goes into the can, and is right once the jelly roll is in here. It would be like here. Of course, the gaps aren't that big, but you have a surface that you need to weld. So you need to weld this to this inside the can. How do you do that? Well, you go through the hole that you left open on the side of the anode current collector. You have access. So you go down that hole and you probably weld it ultrasonically. So basically just very high speed friction, or you can laser weld it, but probably at that stage, they're probably doing ultrasonic welding, and you're just basically welding this center circle here to the inside surface of this circle here. And then you have your positive connection.
So what circle were you pointing to? Because I didn't know what picture you were.
Okay, so I'm looking at the current collector. So I don't know, maybe because I've been drawing a lot on it.
Yeah.
This here, this
Right.
the center of the cathode current collector, which is on springs, is being welded. This surface is being welded to the inside surface of here, from the inside. So
Ricky,
go ahead.
Got to unmute yourself, Ricky.
Guys, let me get back to the picture real quick. So, all right.
Yeah.
All right. So when you were talking about the welding it just to the middle, on the piece where you have the picture labeled top and only the middle is positive, you're saying that the outside beyond the insulator is still negative. So I'm thinking.
Well, it's not connected yet. Because I just explained that I just connected the cathode current collector to the cathode nipple.
To the positive.
So there's no connection yet to the cathode. That's like the next step.
Okay. And my actual question is about the insulator, because you can see that little insulator tab there, right? I'm wondering if that flares out to cover the rest of the inside of the cap to prevent those springs from touching the rest of the can.
Yes, I would very much imagine the same thing.
Okay.
It would be very surprising that, and just so I can clarify, I'm running out of colors here, but let me see if I can maybe, purple, no, what color can I use? Yeah, maybe purple. Here you go. So what we're talking about, maybe I'll draw it on this one. So like this part here, the white part on the inside of the can probably goes all the way to the end, and maybe even like down the side of the can.
Yeah. Okay. That's exactly what I was saying.
Yeah. So okay. Go ahead.
So when you said it goes all the way across, is the can already made like that?
Yeah. So the can,
like
you can see like the cans are like these open on one end, fully open, and they're already closed on the other. And we're
Okay.
missing the cap, like, because there's going to be a cap that
Right.
goes on here, but this we'll address a little bit later.
Okay.
So for now, it's going into the can. We just welded through the hole of the anode current collector, this access hole here. We reached the inside of the cathode current collector. So we reached here to this point to welded to the inside of here. So now our positive connection to the battery is done. Now, what about the negative connections? Well, the negative connections, if we have to look at the anode current collector, and we already saw that we have these 6 like wide flaps that are on the periphery. So if I go here on the can, I'll take the other can here, they'll sit about here. Oh, this is too thick of a pen. Hold on. Take the smaller one. So the flaps, the copper flaps, will be sitting like here on the inside. There's a little gap. Here's another flap. And here's another flap. And they go all around here. Now, these are also welded to the inside of the can. So if here is the inside, well, I can continue. If you can follow, like there's going to be here. This is 1. So I have 3, 4, 5. Of course, I'm not too good, then 6. So they'll be on the inside, and that'll be welded to the inside of the can. So now we have our negative connection. So the casing of the battery is suddenly negative, and the nipple on top is positive, and they're both connected. Does that make sense?
Yep.
All right. I hope I'm covering everything. Sometimes I might forget something until I uncover the next one. Okay, so the next one is we're placing the cap. So now we've welded the cathode current collector to the inside of the nipple of the can, which is the top of the can, and we've welded the anode current collector to the inside of the can on the bottom, because that's what we're calling it, the bottom. And here we need to cap it because it's still all open. So you can see here, I'll take my highlighter, take it yellow. You can see here, this is the can with the little flare. You recognize that from the previous picture. And this right here is the cap that's being pushed in to the battery. That's like a metal disc. So I'm just going to delete it because I want you to focus on something else, which is going to be a bit important later on. You can see this here, there's a little pin. Do you guys see this pin right here?
Yep.
Yeah, okay. So this pin is the center of that metal cap that's being pushed in, and that's going to get crimped. So it's going to be a mechanical sealing, like any of your canned goods. You know, it's rolled metal over metal, and it's done tightly enough that it's completely sealed. So you can still see it here. It's another photo where you see the cap is almost being pushed in. I'll take an even finer pen. You can see there's still a little bit of gap, but the cap is being pushed in to the battery, on the bottom of the battery. I know this isn't much, but I just wanted to point out that little tip of metal because it's going to be important soon. So are we clear here?
Well, that little tip is essentially holding the whole cap in.
Yes, in some way it's holding the lid that's going on and centering it also. Because like the lid, you would have to have it perfectly centered. These machines have to, you can't push the cap and not being perfectly centered. Or else you these machines have probably enough force to distort the thing. So having a positioning system that centers the cap onto the machine and the machine that pushes the cap into the can, this all has to be lined up. But this hole that's in the middle that the pin is currently going through serves a whole other purpose.
Is this something similar to what is currently done with the 2170s, or is this a completely different process?
Completely different process.
Okay.
So much more simple, so much more like first principles, if you want. I know this might sound corny, but when you study this and you think about, there are videos that you can see, like people taking apart 2070s, 2170s, or 18650s, or you can actually see some manufacturing lines that show you a little bit of the process. You'll see that it's much more complicated.
So this is sort of like Tesla's engineering magic at play here, is what we're saying.
Oh, absolutely. Totally. Yeah. If that wasn't clear yet, thanks for pointing it out. It totally is. And I also want to I wanted to point your attention to that little pin that centers in the middle of the cap, but I also want you to take a look at the machine that's putting the cap in. So because it's kind of important. You see, there's a flat here, which is probably just to unscrew it to be able to put a wrench. So you see you have these square flaps, which are about the same size as the rounded sections that are left. So you see there's a rounded section here, and there's machined flats here, because it'll be important in the next slide. So are we clear so far? This whole thing is just putting a cap on the open end of the cell can. Okay, now here, and again, you'll have to zoom in with me. So I'll be zooming in. Let me take a thin pen, and I'll be zooming. Hold on, where's my cursor? Give me a sec. Okay, so here, I'll be zooming in. Okay, I want you to notice, thin pen, there we go. Do you see the hole? Do you see the holes? There's, on some of them, they're more, I took two screen caps because, of course, I had to go frame by frame, but you can see each cap has a hole in it. And this was the pin.
So this is the caps that were just put on.
On the previous machine, and this is where, look at these machines here. Look at how the flats are almost the whole circumference here, the machine, and there's a tiny little sliver of still round. You see? The machines are totally different. So the previous machine was putting the cap and pre-crimping it so it wouldn't come loose. And this machine basically finalizes the crimp of the cap. So the cap is permanent and it's fully crimped. And there's still a little hole left in the center after it's done. But now it doesn't need the centering pin because the cap is in the right place. The previous machine took care of that. Put the cap right in the center and pre-crimped it so it can't move. And this machine, basically, the only thing it does, it finishes in steps because you roll the metal over itself. So it's a continuous process, but it's not doing it in one big yank. As the cells are turning, the machine is applying pressure and it's rolling over these two layers of metal. So if I can maybe draw it really crudely, so I'll draw it up here. So you had the flare in the can that was a bit like this. You had, on the flip side, you also had the flare of the can like this. And maybe I could put the current collectors just so people remember, the anode current collectors were welded here and here, and they have the little springy tabs that go towards the center. And maybe I'll draw the hole in the jelly roll that's about here. And the rest of the current collector was pretty much laying flat on top here, and you had the little springy connections here. And now the lid, maybe take a different color for the lid. I'll take green. So the lid was now placed, and the lid would look something like this. There's a valley, there's a flat section, there's another valley. Here's the hole, the tiny little hole that's left, like this. Oh God, I'm doing better than I thought. Drawing. So this is basically the cap being put on. And once it's done, you'll have the
Are you frozen or
I'm
am I
still
frozen?
moving on my end. Can people see me? All right. Oh no, connection restored. No, sorry, there was a freeze.
Now I see it finished.
So I'm here on top. So basically, these two things are going to get folded over each other. So it's hard. That's going to be very hard to draw. But you'll have, maybe I start with the green. So you'll have the green part is going to be rolled like this. and you'll have the red part is going to be like pinched like inside of it, like this. This is going to be how it's going to be end up rolling, and the can is probably going to be like, yeah, it's
Wow.
but you can look at any like canning machine. It'll do exactly that. So it looks complicated.
Yeah, it can.
But this is basically it. It's turning it slowly and moving the metal one over the other and pinching it so it creates a tight seal. So right now what you're looking at is like once the cap is probably done, like this, there's too much gap here probably. Like it's totally exaggerated, this gap here. But it's to give you an idea of what's happening in these machines. So, and I want to point your attention to this image here that's more at the bottom. That's from Giga Berlin. And this is one of our listeners, subscribers mentioned it, that this cap that you see here, I'm just drawing it from Giga Berlin, the image, you can see the hole and the geometry. What you're looking at here, the cap, is the inside. Mm-hmm. It's not the outside. You can see it's the exact mirror image of the other one. So where the hole is, it's not on a bump, it's in a valley. So this whole thing is going to be facing this side. Here you don't see the current collector. You still see the flags. The current collector isn't there. But you need to flip this cap around to put it on top of the battery.
Well, you can see why the copper sticks up a little bit.
Yeah, those are the flags that get crushed down even further down, and they weld, like we mentioned before, the current collector with the 6 springy things. But again, you can see that the copper side is the anode side, and the anode side is towards the bottom. I know this is, again, confusing because all these cans are bottom up. So the bottom, what we call the bottom, is facing up right now because a lot of the manufacturing, as you saw, we welded the anode, the cathode current collector to the nipple from the bottom of the can, and we put the cap on the bottom of the can, and we did all these operations from the bottom. But that's still, I still call that the bottom, even though it's facing up in all these manufacturing processes, because later on, these batteries are going to flip and the top is going to be actually facing up when we do probably another episode on the structural pack. So any questions so far? Like right now in the process, we have cans that have their jelly roll in there. The cathode current collector is connected to the cathode nipple. The anode current collector copper is connected to the side of the can. We've inserted a cap. We have crimped the side. Now the cell is like closed. There's no way of going back in there except through that little hole right here that's left. Any questions? I think we have a caller. Hold on, we have Ricky.
No, y'all just left me up here.
oh, sorry.
That's fine.
Do you have a? No, you can stay there if there's no other callers. Do you have any questions? Is it clear so far? Are you following along?
Yeah, I was wondering if there was an electrolyte in there.
Oh, good question. You're going ahead. Right now, the battery's still dry.
Okay.
The battery is basically just the mechanical assemblies are done. There's no connectivity, so there's no ion flow between or electron flow in that battery yet possible because there's no electrolyte. So it's dry. But
okay, so the whole allows
exactly. So I'm going to uncover the next section, and this is where you see the machine that actually pumps in the electrolyte. And you'll see it in the video. There's a few frame. I just put a photo. There's nothing particular about that, but all these batteries, so you see it's 6 at a time per tray. So if I call this, this is basically like a tray, and you have 1, 2, 3, 4, 5, 6, and you see there's another row behind here. So it's 12 batteries at a time on each section of this rotating machine that actually it's start up. They put probably like something like a needle in there. They probably draw a little bit of a vacuum. So like the separator gets really well infused and they can fill it fast. And once the battery exit this step, they're filled with electrolyte. There's still a hole at the top. There's filled with electrolyte. And this is the step where after they fill the hole. So I don't think there's probably any questions here, so I'll just go to the next slide. Let me see. I'll scroll over. So basically I can delete the covering. So this is the bottom of the cell that we're seeing. So you can see that the hole is gone. So let me take a pen. So you can see, there we go. You can see this is like the rolled edge right here that was crimped. We have the geometry. So there was a valley, there was a flat, there was another valley, and in the middle there was a little hole. Well, now there's a plug there. That is a plug that has covered. Yes, it was on the side, on the bottom from Berlin.
That was in the other
you
picture,
could see
right?
there was a little little plug.
Yeah.
Yeah, a little pin. Let me go back, because also I have to think of people who will be watching this video afterwards. They won't be able to move around like other people right now can move in Miro. So you have a plug here. And the plug, you can see it's like a little rivet. So it has a narrow parallel thing here, and it has like a mushroom head.
Mm-hmm.
And this thing you can see right now, we see the mushroom head of it, and there's no more hole, and there's a little bit of discoloration. So my theory is that is welded on. Again, probably ultrasonic welding. It might be some other form of welding. It could be resistive welding. I doubt it'd be laser welding. But, I'm not like a manufacturing expert. There's probably a lot of way, but that's when the cell is basically being welded. And the process that they're going through here is basically final inspection, visual inspection of the cell. So there are sensors everywhere, there are cameras, and that's why they're rotating these on drums. So you can see, those are like drums.
I was wondering why.
And each battery goes one at a time and like rolls around, and it's being photographed like thousands of times a second or something like that to see like there's no imperfections during the manufacturing process from the outside. Cool. And this is where you end up with like a finished cell, which is ready for the next step, which is basically like formation. This is where you charge the cell for the first time and you age it at high temperature, at room temperature. And these processes that are the formation processes are basically there to grow imperfections. Like if you had like a little defect in your electrode belt, like for the battery, dry battery electrode process, if you had a defect, the only way to detect it efficiently is to basically, you make the cell, you charge, discharge it, you age it, and then you measure. And if it's nominal, it passes. If it's not, it's rejected. And this is where you get yield, of course, at the end of the whole process. How many batteries are coming out of this process? Good. So this is basically it. I know we didn't cover the dry battery electrode process, and because that's a whole thing in and of itself. So I'll actually hear like the video, like it hasn't refreshed since it crashed, but anyway, people saw it as it was going by. So I zoomed out. So we might talk about the dry battery electrode process. How is it applied to the film and all that? That might be a separate series. And we might do another one for the structural pack. How do we take these cells and turn them into a structural pack? But for now, like the nomenclature, which is the top, the bottom, how things are connected. Are there any questions?
Chris, you can unmute your mic.
Yes, thanks for doing this, by the way. And I don't know if you even know the answer to this, but I'm just kind of throwing out something hypothetical. So, and it would be based on kind of your own kind of hearing from people inside. Based on what you outlined here as far as the actual manufacturing process, can you point out which steps in the process they're currently having issues with respect to yield as you've gone through and kind of outlined the beginning to the end, if you know, and if you're allowed to talk about it?
Yeah, so the yield, like each step in a manufacturing process has a yield. It's important to understand this because I went through a lot of steps here. like inserting the jelly roll, welding this, welding that, all these steps, like filling with electrolyte, all these steps have a throughput and have a yield. So there's how many you can go through, how fast you can go. And for example, the crimping, like closing the lid on top of, on the bottom of the battery and crimping it, that has a throughput, how many you can do, like in a certain amount of time. And there's a yield, how many of these crimps pass inspection, for example. So right now, all these steps have very, very high yield. On the battery, how the dry battery electrode is being applied to the film, this is where there's a complication. Like crimping, you can imagine any canning facility has very high crimping with very, very high throughput and very high yield. Like they don't throw cans of food because the crimping once, like has only like a 50% yield or something. That doesn't happen. So this is where the challenge is. And the challenge was in, and I don't want to get too much into detail because we'll do that in another episode, but the way the film, I think people have a misconceptions of how they're doing the dry battery electrode, putting it onto the film. And this is where the mixture was, you remember Elon mentioned that it was like denting the rollers. And we had mentioned this in a previous episode where the mixture, there's the temperature, there's the adjuvants, there's the active material, all this stuff. And there's the pressure of the roll and the speed of the roll. The mix was not fluid enough, was not shearable enough. So as they were increasing the speed, the mass was not moving out of the way fast enough, and it was a bit like moving the rollers, like denting them, not like physically like denting them, but moving them out of the way. And of course, they fixed that. So the yield overall, I can't tell you the numbers, but they're very, very good. And all of these things were like engineering problems, like adjusting the temperature of the batch, adjusting its viscosity and everything so it could move out of the way at higher speeds. So there's no problems there.
So, but there's obviously, and again, this may require a comment that you can't make or maybe don't know, but there's obviously, they haven't reached a yield that allows them to move forward with, fully deploying production equipment in Berlin, for example, and in Austin. From the beginning. In other words, as we've already heard, they're going to use the pilot line in Fremont initially for Austin, and they're going to do 2170s in Berlin from China.
Yeah, so I can answer that. So you got to understand, like, there's the pilot line and there's the Roadrunner line. Like, they produce the exact same batteries. They go through the exact same processes. The only difference is that the Roadrunner line uses a much wider mother roll, which is like the 16 roll we mentioned at the beginning of the episode. That is those 8 black strips that are cut down into 16 strips. And it's the speed at which that machine goes. And this is where that machine is not a problem, but there are engineering issues to be fixed as you're increasing the throughput. First of all, there's all these steps that I mentioned in between. Those steps has to follow. You can't have like dissimilar throughputs, or else you have to build inventory, buffers in the middle of this process. So when you're making the foil go faster, like you're getting 16 rolls wound at the end of that process faster, which have to go to winding jelly rolls faster. And these jelly rolls have to get wound faster and then inserted into cans faster. And all this process has to be like accelerated. And this is where along all these lines, they're solving small engineering issues that's entirely normal for any manufacturing process. Because once you make one go faster, that in that process, there might be issues, but then you might uncover issues in somewhere else down the line that, suddenly the yield isn't that good, let's say for crimping, because like the crimping machine is not, set to run at that speed. And then you have rejects of the crimping, but then you just fix that crimping issue and suddenly the yield is back where it's supposed to be. But you can't like just go full on one end and, how you uncover these problems is by going incrementally faster and faster and faster and figuring out those issues. And since the engineering solutions to these engineering issues may modify what the machine looks like in the end, because a part might be different, it might, have changes, there's no point in deploying big lines at Austin or at Berlin until that machine is like perfect. So until the Roadrunner machine is perfect, or as close to perfect as a whole manufacturing system can be, it's not going to be like replicated all over the place, because that would mean them updating all those lines. But right now, the pilot line is producing cells with very good yield. So they're stockpiling them. Does that make sense? Did you see like the difference of making a pilot line that can actually produce real world cells, no problem, and then going to a high speed, high throughput system that does exactly the same thing, but suddenly you uncover new problems because the pilot line wasn't going that fast.
Right. Yeah, that makes perfect sense. So thanks.
Thanks a lot. Any more questions? Oh, we have a whole queue. I wasn't seeing it. Okay, next up. Who's next? Speak.
Stefan?
Speak now or forever hold your peace. My app is a bit sluggish. Go ahead.
So this actually brings me back to it. First off, thanks a lot. That really kind of walking through that whole process, understanding that the whole can is negative except for the top, makes me understand that picture from the Berlin walkthrough where you can see the top layout of those pieces falling on it, to how one negative side attached to the other positive side in that layout.
Mm-hmm.
That makes me think that they're grabbing all the current from the top. So there's obviously a reason for that, right? Why would they have everything on the top? What are they doing with the bottom of the cell?
Hold on. I think you misunderstood. Like the nipple is only connected, the top of the cell is only connected to the cathode current collector, which is the aluminum side. That's the positive of the battery. Like every battery, has a positive end and a negative end. Like the negative end is the whole rest of the can, and it's connecting at the bottom of the can throughout the circumference. And this is where the most of the heat that's generated within the jelly roll will be coming out. Like the thermal conductivity of copper is higher than aluminum. And as you can see, like on the copper side, it has so much more welded area to the inside circumference of the can than the cathode has on the nipple.
You know which picture I'm talking about, where they showed how they're all connected up on top at Berlin?
At Berlin, there was no current collector. You were only seeing...
When they showed all the batteries laid out.
Yeah. You're talking about the pack. Yes, on the pack. Yes, totally. Yeah. I totally agree. Like on the pack, that's the pack current collector, not the cell current collector, the pack. It's welded to one end is welded to the nipple, and the other is to the side of the can, which is the negative side. And this is where I was saying, like, there's basic, like, to my mind, there's like three functions that you need to solve with batteries. So you have three faces on a battery. You have the top face, where the nipple is. You have the bottom face, where we saw that little hole and that plug being inserted. And you have the circumference of the can, like the cylinder. So you have three sides to a cylinder. And you have three functions that you need to perform with batteries. You need to connect them electrically, and this is going to be done through the top of the cell. Then you have a cooling function. You need to cool these cells somehow, and they're going to be cooled by ribbons on the circumference of the cylinder, on the side walls of the cylinder. And the third function is safety. If something goes wrong with a cell, like a thermal runaway event, and the pressure starts building, you need a way to basically have that battery being able to vent those hot gases and materials in a safe way where it doesn't propagate to the adjacent cells. And this, in my mind, will be towards the bottom. But if you put like the current collection on the pack side on the same side as the safety, it doesn't make any sense, because like that, let's say battery exploding, those hot gases will be like in contact with the current collector of the whole pack. And then you could short circuit stuff and make the problem way worse. So you need to isolate these three functions, and you have three sides to a cylinder. So it makes sense that each side of a cylinder gets only one function, because it's also hard to cool something as you're doing current collection. You know what I mean? It's like, so three sides, three function, each side gets a function. That's how I see it.
Got it. So the way that you were saying it had more welds on it, you're thinking that the battery is almost made to have a weaker point at the bottom?
Yeah. I'm thinking that plug is designed and welded in a way that makes it, once there's like overpressure inside, because you got to understand, once there's a thermal runaway event inside a cell, there's a lot of gases and steam and all sorts of stuff that being created in there. And you need to like flush it as fast as possible. And you need to, ideally, you want it in a certain direction, very predictable. So you can design around the safety functionality I was talking about. And I think that's like the ideal place to do it.
No, I like that. All right, thanks.
No problem. Who's next? Ben? Ben, going once. Going twice. Can you unmute? Okay, we're going to skip over Ben. Oh, is Ben here?
Yes. Hi, Alex. Thanks so much. I had a question about the springiness of the current collector.
Mm-hmm.
So what are your thoughts now, having gone through these details? Like, is that having to do with being able to weld well the outside of those springs? Does it have to do with fitting in insulation or heat control or vibration? What are your thoughts on that?
I'm still not 100% sure. I know that from a manufacturing standpoint, having flexibility, like not having something that's perfectly rigid because everything has tolerances, it might also help in that sense. But I've been reading a lot of scientific papers about the effects of vibrations and shocks on lithium-ion cells. And most of the tests were done, of course, on 18650s and 2170s. And I'm thinking like this massive roll might have like different needs and be able to, have these softer connections. So you have the electrical and thermal connections being done like rigidly because it's welded, but then it isolating the jelly roll from the can itself. And the can is, like part of a structural pack. So it's basically one big component of the car. I think there might be something there. I'm not 100% sure. Still have to think about it and brainstorm with other engineers as to why that could work. And also, it might be also a way just to isolate, as Jordan Giesecke was mentioning in our previous 4680 episode, just like giving a space between the top and the top of the can and the cathode current collector, and the bottom of the can and the anode current collector. Just a way of like keeping them like separate, with taking into account the manufacturing ease of having something that can be flexible, in the sense that even though maybe your jelly roll is like a few microns too short or everything, you're not straining anything because there's a certain amount of give in there to be able to accommodate manufacturing and better yields. It could be a combination of a whole bunch of things.
So in practice, it is mostly flattened, but to your point, it could have a little bit of wiggle room for vibration or for...
Yes, those springs, like before you weld them, like positioning them, having these on like a flexible surface gives you for lack of a better term, like wiggle room to position it. So if it, let's say the positioning and the welding of the cathode is not like, no manufacturing process is 100% precise. There's always a plus or minus. And these pluses or minus, in manufacturing is what, determines the yield at the end. If you're over that tolerance, you might, these problems might stack up. So if the welding process of the cathode to the nipple has a plus or minus, and the next step is the welding of the cathode, while having a bit of yield because it's on flexible structures, might just eliminate this whole tolerance problem and just increase yield without compromising anything of the quality or the performance.
Thanks so much. Thanks very much.
No problem.
I really appreciate the presentation.
Yeah, thanks a lot. Next, Idan, you're up.
Hey guys.
Yep.
Thanks for the presentation. Great presentation. My question is about the copper tabs. They get kind of squeezed on the bottom side of the anode. So I'm kind of wondering, what would the machine that does this step look like? Because it seems like they have to be squeezed simultaneously and uniformly from all directions. Does that make sense?
Yep. Well, first of all, I just want to clarify this. We've always, like what I call the Rosetta of flags, all laid down. The cathode side looks exactly the same, but it's made of aluminum. So it's shiny metal, white metal, instead of red copper metal. So both sides are identical. Like, my thought is to achieve like this Rosetta, you would need to lay down these flags from the outside in. So you would probably have a machine that has a certain like conical type shape, and probably also turning, because they're all laid down depending how you look at it, but they're either all clockwise or counterclockwise. So basically something that pushes in and starts pushing the outer flags that are on the periphery and starting to lay down, and those push against the next row that pushes against the next row, and so on and so forth, until you get to the center hole of the jelly roll. That's, I think, the only way I could see them, that they could like lay them flat, all in the same direction and without breaking them. You still got to remember, these things are very, very thin. Jordan was mentioning that it's around 10 microns, and we're talking a red blood cell, I think, is 8 to 9 microns in diameter. So these foils are extremely delicate. So you can't just like,
you need to be careful not to tear them off. Right?
Exactly. So the way you're lying them, it can go fast, but it still has to be delicate.
Okay, thanks. I also have a bunch of questions that more relate to the path, but maybe I'll patiently wait for that.
Yeah, come back for that episode. We're still working on it.
Okay.
No problem. Next up, Aurelio.
Hey, everyone. Thanks a lot for the presentation, Alex.
No problem.
I was just wondering about how the electrolyte is actually injected into the battery. Or actually where the electrolyte is injected. That would be more my question.
Yeah, so the electrolyte, from all we can tell from these photos, once the bottom of the can has been placed and crimped, you have like an injection system that puts it in the middle of the battery, that goes through that tiny little hole, and that basically injects it into the can. My thought is they're probably drawing a bit of a vacuum, so the electrolyte will be absorbed quicker as it's being injected. So it's not like doing it like an overpressure. Like, if you take a bottle of water and you fill your mouth with water and you're trying to push it in, you're going to get resistance. But if you draw a vacuum in the bottle, then the liquid actually wants to go in there because there's negative pressure. Yeah. So that's...
So if we look at the second image you have in the presentation, there's so we see the cathode film, the anode film. So anode is the copper, cathode is the aluminum.
Yep.
And we have this, is it the white thing, is it the separator?
Yes, so you have like two separators, and you have on top of that, I think at the very end, when they finish rolling it, you have like like, for lack of a better word, like plastic bag, white, and then you have the two blue tapes on each end.
Mhm. Yes. And so the electrolyte would actually go like between the separators, essentially.
Yes, the separator is what absorbs the electrolyte, and this is what allows ions to move.
I see. Okay. Got it. Thanks.
Perfect.
Thank
no
you.
problem. Next up, and that's going to probably be a last caller. David, you're up.
Yeah, hi there. Thanks for putting this together. Very interesting. I might have, I've been kind of in and out through this conversation, so you might have gone through this, but hopefully you could bear with me and do it again if not. But there's so you've got the cathode current collector, and when that gets inserted into the can, that has to be welded to the nipple, and there also needs to be a separator in order to make sure that doesn't ground out to the outside of the can. And that looks like that's happening upside down. I saw you drew some of that. Could you go through how you sort of see and how you think that doesn't become a leak point too from that separator, how they maintain that pressure or crimp there or anything that's
my best guess for that is and it's looking a little bit at the manufacturing process. So I'm guessing they're making, first of all, everything starts with like a sheet metal, because that's like the least expensive thing you can buy. So it's rolls of sheet metal. And they probably like cut out circles, and they deep draw these circles to make the shape of the can. And the can on one end, it's very clear. It's like flared at the top, ready to receive the cap. On the other side, it's probably just a little hole in the center. And this is where they probably put a plastic, an insulating material on the inside that maybe I can draw it. Are you on Miro right now?
Yeah.
Okay. So,
I imagine it like a plastic washer, basically.
Yes, exactly. So
kind of like a knife.
let me sketch what I'm thinking. So I'll be, for anybody that's just follow my pointer, I'm around here where Jessica's found me. So where Jessica and I are on the Miro. So I'm guessing the can, like if we're putting it right side up, we have the flare, we have the can going up. There's a little curve here. There's the flat part. There's probably a little hole once it's manufactured. There's the other curve. It's going down, and there's the flare here. So my guess is I'll just take the highlighter and the washer. Let's put it gray. I'm guessing there's like a type of washer. Well, no, that's not very visible. Let's put it darker gray. Yeah, so my guess is that there's a plastic thing that goes like this.
Yep.
About like this. And then the nipple, I'll draw it, let me use another color like blue. I'm guessing they're putting like something that looks like a rivet in the can, like this. And then what they do is basically swage the rivet. So they flatten out this part. So this, like even the plastic, everything gets crimped. So if I go back to the gray will lay flat here because of the mechanical pressure, and they'll swage the rivet, and the rivet will, end up being like this.
Yeah.
So basically you have immense pressure. Immense pressure pinching the insulator between that red steel of the can, and that basically becomes like impossible to break, like to leak or anything.
And then, you think they're doing this before they insert the jelly roll?
Oh, absolutely. You can't do that.
Yeah.
Yes, because you need the whole can finished. And then to finish like...
Right, but then the connection from the aluminum cathode current collector to that swaged nipple, that's just a contact, or that has to be...
that's welded. So let me draw just so we're talking about the same thing. So let me draw in purple the jelly roll. So the jelly roll goes, once all that operations are done, the jelly roll comes in here, goes in. And of course, I'm leaving big gaps here, just so it's clear. And the current collector, the cathode current collector, I'm going to use green. We know that it's laying flat here on top of the flags. So let me, hold on. It's not super clear. So yeah, I'm going to do it a little bit thicker, but we know there's also like little arms, right? Like little springy arms that go towards the center. And this gets welded. And how does it get welded? Well, it gets welded because the jelly roll here in the center, I'll put it in dashed lines, has a hole. So there's a hole here in the middle of the jelly roll. And they come in with a tool, and I don't know if I can maybe draw the tool with a rectangle. They come in with a tool. Let me black and make it a little bit wider. Let me zoom in so it's wider. They come in here with a tool, and they press the center that's on springs to the swage inside nipple. And I'm thinking it's probably ultrasonic welded. And then the connection is done. But yeah, the whole nipple and insulator, that's already done. Like before the jelly roll comes in, that whole part is done. They just insert the jelly roll, and then they come in with this tool in the center. And hold on. So this tool comes up.
And the ultrasonic would be able.
Yeah.
Go ahead. The ultrasonic would be able to do that, you think, without compromising the separator or the insulator. I guess we should put it, the gray insulator.
Yeah, because it's not even touching it. If you look at what I drew, like the insulator's on the other side of the swage nipple. So
and there's no heat that's coming from the ultrasonic welding.
No, it's very fast. And yeah, there's no real heat being generated there.
Okay. That makes sense. Thanks.
All right. All right. So I think, so we got another question. Okay, let's take another one. Let's make this our last one. You're up, Idan.
Yeah, thanks. Coming up again, kind of thinking, following David's question, and putting aside the dry battery electrode process, which wasn't discussed, what would be the primary differences in your mind between this process and the process used for 2170s and 18650s?
Oh, it's completely different. It's night and day, both from how the electrode material is put onto the foil. One is a wet process with solvents, the other one is dry. And then also how the can is assembled and when the electrolyte is filled. Like all these cans, they have the electrolyte filled before the cap is being secured. Whereas here you see it's actually the opposite. The can is finished mechanically before the electrolyte is even put in the can. So it's totally different.
So totally
and
different
it's
process.
Much more delicate because if you remember, you need to weld not only during the process, you need to weld the tab, like in a tab design. This is tabless. The 4680 is tabless, but in the tab design, you need to weld like pretty heavy metal compared to the thickness of the foil. You need to weld something then, and then you need to weld that to the cap, to let's say the nipple. So you're leaving steps toward the very end when it's very hard to manipulate these tiny cells and these fragile components. You're putting it at the worst possible time to do these connections. Whereas here, if you look at this whole process, there's nothing that seems like complicated. I know it was hard to explain it, but once you understand how it goes together, you see that there's no real chance of having any issues. Everything has an access for every operation, and every operation is in the right step to allow the second operation until the end, until you have a finished cell. There's no point where there's a delicate operation in there, if that makes sense.
Okay. Yeah, sure.
Yeah, no problem. Well, folks, we've been going at it for an hour and 20 minutes. So I want to thank you. Lots of people in the room. I think we were holding steady about 100. So I really appreciate people enjoying this and spending a Sunday afternoon with us.
No, and thank you for putting it together. It's interesting.
Yeah, thank you so much, Alex.
Yes,
Yeah,
thank you.
I think we will do I think we will expand on the series with further episodes, as you said, like the dry electrode and the structural battery pack. I think that would be some good topics to talk about too.
Yeah, and if you have questions on this episode, it will be published. It's going to take a little time to be available on YouTube because we have to put it together. But
rendering takes a while.
Yeah, rendering takes a while, and uploading and everything. So, but if you have questions like on Twitter or whatever, feel free. We're going to try to answer them as best we can. Okay, so thanks a lot, and closing the room. Catch you soon. Subscribe to XPod for future episodes. Thanks a lot. Bye-bye, everybody.